Hello everyone, this is Manohar Reddy, Assistant Professor, Department of Cybersecurity, Institute of Aeronautical Engineering College. So today I am going to discuss about the next topic is fields and its types. So we already said that different types of algebraic structures or algebraic systems formats. So in that groups and rings and fields. So these are all different types of algebraic structures or algebraic systems. So today we are going to discuss about fields. So see here, a field indicates f, a field indicates f, and f with plus comma dot operator, f with plus comma dot operator. And here a commutative ring with identity r plus dot operator, it satisfies all of the axioms, so that axioms are nothing but associativity, identity, and universe, and commutativity properties. So it should satisfy these all the axioms, and that r plus is as to be abelian group. So a commutative ring. So commutative ring is nothing but what? A ring, it satisfies a plus b equals to b plus a with respect to the addition operation. Similarly, a dot b equals to b dot a with respect to the multiplication operation. So then it is said to be commutativity ring, right? So commutativity ring with identity r plus satisfies all the axioms of this one, and that is to be abelian group. So now the original definition comes here. So field is nothing but a field is a structure of R. So generally it represents what? So a structure, it represents like this way. So field is nothing but the form of the ring, so that is nothing but a structure follows same like as ring. That's why a structure R plus dot, where plus and dot are binary operations on R, is a field. If A1 to A4, that means addition operation with respect to the associativity, identity, universe, and the commutativity with respect to the addition, as well as multiplication with respect to the multiplication, associativity, identity, universe, and commutativity. And distributed law is also holding, and 0 not equals to 1 should be followed. So if it is following like a1 to a4 with respect to the addition, so addition and multiplication, m1 to m4 with respect to the multiplication, and distributive laws holds. So if it satisfies all the conditions, then this structure is called as field. Right? So here you can see a1 to a4 means associativity, identity, universe, commutativity with respect to the addition. And m1 to m4 means associativity, identity, universe, commutativity with respect to the multiplication. So this can be expressed in a more modular way as follows. So r plus dot is a field if and only if it is said to be the abelian group as a ring. It is said to be the abelian group or a ring, and it is an abelian group, and distributive laws holds. So with respect to the addition, with respect to the multiplication, and with respect to the distributive laws, if it satisfies all the conditions as a like a ring, then it is said to be the field. So field indicates f, star, f, plus, dot. The only the thing is different is ring and fields. Ring and fields are both algebraic structures, but the ring can have only the square shape, of the form, and field contains the formation in the ring. So the structure is follows like this only. And for the ring, it does not holds in this distributive law, but for the fields it should follows this all the respectable addition operations and all the respectable multiplication operation with respect to associativity, identity, inverse, commutativity, and all. Similarly for the M1 multiplication also, associativity, identity, inverse, commutativity properties, right? So then it is said to be field. See here, the ring with a single element 0 would technically qualified as its field. A ring, so this is a ring. If you take this is a ring with a single element 0 or 1, or you can take any of the element, and would technically you can say that it is a field. Means if it wants to become a field, it must having some elements in the ring. But if you don't have any elements in the ring, it does not qualified as a field. And it is said to be empty field, right? But at least any one element in the ring is to be qualified as a field. At least one element in the ring is to be qualified as a field. So a field must have more than one element. A field must have more than one element. At least it have some elements, right? And in a field we must have 1 not equals to 0. So if there is an element x not equals to 0 in a ring with identity, then you can rewrite it as a 1 dot x equals to x not equals to 0 equals to 0 dot x not equals to 0, and that means 1 dot x equals to x is okay, 0 dot x equals to 0 is okay, but these two are not equal. That means you are not going to say this identity element 0 with respect to the x and identity element 1 with respect to the x is not equal. So this is the way you can understand here. And the standard examples of fields are the rational numbers and real numbers and the complex numbers. So rational numbers and real numbers, complex numbers, these are all some best examples or standard examples for the rational for the fields. And the integers mod p for a prime number p, So these are all some best examples or standard examples to show that all the rational numbers are to be the field, or real numbers are to be the field, or complex numbers are to be the field, or else integer mod p, suppose a power mod p, a power p or a power pi of n equals to 1 of mod n. So like this all these type of expressions, or you can say that fields. So this type of expressions, this type of rational numbers, this type of real numbers and complex numbers, these are all you can say that it is standard examples to become a field. And a field f comma plus comma star is a structure of elements with two binary operations, addition and multiplication, such that if a comma b comma c are the elements of f, and it should be satisfied all these conditions. That conditions are nothing but closure, associativity, identity, inverse, commutativity with respect to the both addition and multiplication. This is what we mentioned in the previous slide here. So A1 to A4 with respect to the addition, associativity, identity, inverse and commutativity with respect to the addition should be satisfied, and associativity, identity, inverse, commutativity with respect to the multiplication should be satisfied. Along with that, distributive law also holding that, and it doesn't contains empty elements. It doesn't contain empty element. That means it should contain at least more than one element. So this is what we mentioned here, right? So that is the way you can understand this field. So field is a form of ring, and it is at least one element of the ring is to be qualified as a field, right? Okay. Then next, finite fields. So we know that finite group, right? So finite field, finite group. So finite is nothing but you can count the number of elements. So finite field which contains number of p power n elements. So suppose you can take f equals to 1, 2. Then you can set that f of p power n, that nothing but f of g of p power 2. So that is second order of the field. So two elements, if you have two elements, then you can say that two elements of that field. So that follows p power n elements or order of a field is also called as Gaussian field. And this finite field is also called as Gaussian field. So finite field contains countable number of elements, and that it is also called as Gaussian field. So if it indicates Gaussian field, it indicates like this: Gaussian field of p power n, Gaussian field of p power n, where gf is a Gaussian field, and p power n is nothing but the order, the order are the number of elements in the set, in the finite field. So if the field contains only one element, then you can rewrite it as g of p. So that is nothing but only one element or one order of the field. The order of the field is only one. And if n equals to 2, if n equals to 2, then you can say that the order of the field is 2. So g of p power 2, that equals to, you can take two values 0, 1. So like the way you can take it. So we'll see one example. Show that all the integers of order 5. So show that all the integers of order 5 is a finite field with respect to the both addition and multiplication. So with respect to the multiplication and addition, we are going to show that the order of 5 means gf of p power 5. P power 5 is a finite field. You want to show them, right? So we know that finite field is nothing but countable number of elements. If it is having only one element, then the order of finite field is said to be only 1. If it is having more than one elements, then it is said to be finite fields. That means countable number of fields. If doesn't have any elements to countable, then it is said to be empty field. So the finite field is also called as Gaussian field here. So Gaussian field indicates g of p power n, where p power n indicates the number of elements in the field. So now we'll see one example. Show that all the integers of order 5. With respect to the both addition and multiplication. Let us see that example. So we'll take all the integers z equals to 1, 2, 3, 4, 5. So this is what we are having all the integers. So we need to show that with respect to the addition operation as well as multiplication operation, we need to show that a finite order of, so it is ordering only 5, so that we can take only 5 elements. So including 0. So 0, 1, 2, 3, 4. Like that, you can take all the 5 elements. So Z equals to 0, 1, 2, 3, 4. So the addition operation. So first of all, you need to perform addition operation, because they are saying that our finite field with respect to the addition, with respect to the multiplication, right? So with respect to the addition, with respect to the multiplication. So before going to show this, we need to confirm that it should satisfy some properties. It should satisfy some properties. So closure properties and associativity property, identity property, inverse property, and distributive loss property. So we need to show them in the form of addition operation as well as multiplication operation. So first of all, we need to show that as additive operation. So additive operation. So we need to show that. So take these elements with a modulo of 5. So order of field is 5, so that you can take addition modulo 5, and 0, 1, 2, 3, 4, you can take 5 elements, and similarly 0, 1, 2, 3, 4, you can take 5 elements, right? Now you can do what? Addition operation. So what? 0 plus 0 is nothing but 0, 0 plus 1 is nothing but 1, 0 plus 2 is nothing but 2, and 0 plus 3 is nothing but 3, and 0 plus 4 is nothing but 4, right? So now you can set that closure property is satisfied because the top row of the element is same as the first row, first column of the elements are same. So you can say that it is a closure property. And we'll go for the next one. 1 plus 0 equals to 1, 1 plus 1 equals to 2, and 1 plus 2 equals to 3, and 1 plus 3 equals to 4, and 1 plus 4 equals to 5. But you are not having that 5 element in the set, right? We are not having the 5 element in the set. So what we need to do? We need to perform the additive operation. We need to perform the additive operation. So 5 divided by 5, that equals to, you will get the remainder is 0. You will get the remainder is what? 0. So that you can place 0 as this element. 0 as this element. And for the next one, 2. So 2 plus 0 equals to 2. 2 plus 0 equals to 2, and 2 plus 1 equals to 3, and 2 plus 2 equals to 4, and 2 plus 3 equals to 5, and 2 plus 4 equals to 6. So 5, 6 are not having the elements in the Z. So what you need to do? You need to replace them with 5. In place of 5, you can replace with 0, and in place of 6, so you can perform the operation, additive modulo operation. 5 1 5, and the remainder is what? 1 you will get here. So you need to replace 1 instead of 6. So you can replace them. And similarly, you can see here 3 plus 0. 3 plus 0 is nothing but 3, and 3 plus 1 is nothing but 4, and 3 plus 2 is nothing but 5, and 3 plus 3 is nothing but 6, 3 plus 4 is nothing but 7. But 5, 6, 7 are not having an elements in the set, right? In the set. So you can replace this 5, 6, 7. You can replace this 5, 6, 7 with the help of, by doing this division operation. So what you will get here? 5 1 5, and the remainder is 2. So in place of 5, you can rewrite 0, and in place of 6, you can rewrite 1, and in place of 7, you can rewrite 2. You can rewrite 2. So these are the operations. These are the operational values. And similarly for the 4. So 4 plus 0 is what? 4. And 4 plus 1 is what? 5. And 4 plus 2 is what? 6. And 4 plus 3 is what? 7. And 4 plus 4 is what? 8. 4 plus 4 is what? 8. But we doesn't have any this 5, 6, 7, 8 elements in the set, right? 5, 6, 7 elements are not in the set. So that we need to replace them with replacing values. So 5, 6, 7 already we know that. So for the 8, you need to divide 8 with 5. So what you will get here? 5 1 5, and 8 minus 5 3. So you need to replace 3 in place of 8. You need to replace 3 in place of 8. And similarly, you need to replace 0 in place of 5. You need to replace 1 in place of 6. You need to replace 2 in place of 7, right? And here 3. So this is the way you will get all the closer values. Now you need to tell that. So with the respective addition, what you need to show? With respective addition, we need to show closure property, we need to show identity property, and we need to show inverse property, and we need to show commutativity property. So commutativity property. So you will see here the first row of the elements is same as the first top row of the elements is same as the first column elements, so that it is said to be the closure property. Then it is said to be the closure property. And similarly you can tell that identity property. So a plus 0 equals to a, and a plus b, anything you can take it, a plus a equals to 1, or b equals to 2, or c equals to t, any values you can take it. So for that you can take a equals to 0, so a plus 0 equals to a. So the identity element 0 is exist in the integer set, so that the identity element 0 is existed in the set, so that we can say that it is a identity property satisfied. It is satisfied identity property also. And inverse property. So for the inverse property, additive inverse, see here the a equals to 0, 1, 2, 3, 4. But the inverse is nothing but what? So the positive integer a, the inverse of that element, the inverse of element is nothing but minus a. Minus a is the inverse. Minus a is the inverse of that element. Inverse of that element. So what we need to do here? So a equals to 0, 1, 2, 3, 4. So the inverse values are, how we are going to obtain this inverse values means, see here, the respective of this addition operation, so where you will get the zeros actually, so we get the 0 in place of 0, so that's why you will get here. And in the second one, for the 1 we need to get 0 is here, so like the way you can write 4. And similarly for the 2, where you will get 0, so third place you will get the 0, and here the fourth place you will get the 0, and here third place you will get the 0, and for the third option you will get the 0 in the second place. So and last for the fourth one you will get the 0 in first place, right? So the first row you will get the 0 for the fourth column. So this is the way you can understand the inverse of that elements existed in the set. So 0, 1, 2, 3, 4. Here also you will get 0, 1, 2, 3, 4. So that you can say that it satisfied this additive universe. So it satisfies closure property, it satisfies addition identity property, and it satisfies inverse property also. And last one, commutativity property. So 0 plus 1 you can take it, and 0 plus 2 you can take it, 0 plus 3 you can take it, 0 plus 4 you can take it. That belongs to the same set, so that you can set that it is a positive integers, and it is a additive universe. So now closure property satisfied, identity property satisfied, and the inverse property satisfied, and also the last one is what? So commutativity property satisfied. So with respect to the addition, so that the phi order, so that the order of phi of a finite field is to be the finite field. So order of phi is a finite field to be satisfied. So like the way you can say that. And we'll see the multiplicative module also, for the multiplicative module. So see here how you will get multiplication modulo, and you can prove that multiplicative modulo with respect to the associative, commutative, and identity and the inverse properties also. So see here, so first of all you need to take that phi order means, so 0 you need to take, and 1 you need to take, 2, 3, 4. So here the operation is what? Star operation with respect to the multiplicative, or modulo of 5. Modulo is 5. So 0, 1, 2, 3, 4, 5 values, and 4 values, and 0, 1, 2, 3, 4 values you can take it. right? Now you can do the multiplication operation on this all the set elements. So 0 into 0 is nothing but 0, and 0 into 1 is nothing but 0, and 0 into 2 is nothing but 0, and 0 into 3 is nothing but 0, and 0 into 4 is nothing but 0, right? So the first elements are all set to be 0. The first elements are all set to be 0. And next one is what? 1. So we need to multiply with 1 into 0. 1 into 0, 0. 1 into 1, 1. 1 into 2, 2. And 1 into 3, 3. And 1 into 4, 4. 1 into 4, 4. Right. Next, we'll go to the 2. So 2 into 0. 2 into 0 is what? 2 into 0, 0. 2 into 0, 0. And 2 into 1, 2. 2 into 1, 2. And 2 into 2, 4. 2 into 2, 4. And 2 into 3, 6. 2 into 3, 6. And 2 into 4, 8. 2 into 4, 8. But you have to observe here. So what? So 0, 2, 4 are existed in the set. 0, so what is the set actually? 0, 1, 2, 3, 4, right? So in this set, we are having 0, 2, 4. So 0 having, 2 having, 4 having. But 6 and 8 doesn't have. 6 and 8 doesn't have. So what we need to do? We need to replace that 6, 8 values with the modulo operation. So how we'll see? So for the 6, if you divide with the 5, what will get? 5 1 is 5, and 6 minus 5 is 1. So that you can replace 1 in place of 6. You can replace 1 in place of 6. And similarly for the 8. So for the 8, what you will get? So 5 1 is 5, and 8 minus 5 is what? 3. So the 3 is the remainder. So you can replace 3 value in place of 8. You can replace 3 value in place of 8. So that you will get 1 3. You will get 1 3. And for the 3 also, you can see 3 into 0. 3 into 0, obviously 0. And 3 into 1, 3 into 1, 3. 3 into 2, 6. And 3 into 3, 9. And 3 into 4, 12. 3 into 4, 12. So here 0, 3 existed in the set. 0, 3 is existed in the set. But 6, 9, 12 is not existed in the system. It's not existed in the set. So what you need to do? You need to replace them values by doing multiplicative modulo. You can do that. So what you will get? For the 6, we already done it. So the value is what? 1. The value is what? 1. And for the 9, so 5, you can divide 9 with 5. You can divide 9 with 5. 5 1 is 5. So 9 minus 5 is what? 4. 9 minus 5 is what? 4. So you can replace 4 in place of 9. You can replace 4 in place of 9. You can replace 4 in place of 9, right? And the next one is what? 12. So 12. So we need to divide 5 with 12. We need to divide with 5, 12. So what we will get? 5 2 is 10. 5 2 is 10. And the value is remainder is 2. So remainder is 2. You can replace that 2 value. You can replace the 2 value in place of 12. In place of 12, right? So these are the replacing values by doing this multiplicative modulo operation. Multiplicative modulo operation. So next one, 4 into 0, 0. And 4 into 1, 4. 4 into 1, 4. And 4 into 2, 8. 4 into 3, 12. And 4 into 4, 16. 4 into 4, 16. So 0, 4 are existed in the set. Yes, 0, 4 are existed in the set. But 8, 12, 16. 8, 12, 16 are not existed in the table. Are not existed in the table. So what we need to do? We need to perform the multiplicative modulo on these 3 numbers. 8, 12, 16. We need to do the multiplicative operation. So how we will get? For the 8 we already done. So the remainder is what? 3. So if you divide 8 with 5 modulo, what you will get? The remainder is 3. Right? And for the 12, so see here 12, we get 2 as a remainder. So you can replace directly 2 in place of 12. So you can replace directly 2 in place of 12. And for the 16, so for the 16 how you will get, so you can divide 16 with 5. So 5 3 ja 15. 5 3 ja 15. So 16 minus 15 is nothing but 1. So the remainder is 1. So the remainder is 1. So this is the way you will get all the values. This is the way you will get all the values. Now what you need to do, we need to satisfy all the properties by doing this, by showing this composition table. By showing this composition table. So first property is what? Closure property. First property is what? Closure property. Closure property with respect to multiplication. So with respect to multiplication. So closure property is nothing but what? The first a dot b equals to b dot a equals to the value same, and that belongs to f. That belongs to f. Right? That belongs to f. And second one is what? So already we having this one. So the row 0 1 2 3 4 and the top row is to be same, so that you will get the closure property should be satisfied. Then you can say that closure property should be satisfied. And next one is what? Second one is identity property. So identity property is what? So a dot 1 equals to a, or else you can say that a dot a plus 0 equals to a. So this is additive and this one is multiplicative. So a dot 1, so you can take 0 dot 1, you will get 0, and that 0 is element in the set. Suppose 1 dot 1, you can take 1, then 1 is already in the set. And if you take 2 dot 1, that equals to 2, it is already in the set. And 3 dot 1, you can take it as 3, it is already in the set. And similarly 4 dot 1 equals to 4, that is already in the set. So you can take like a equals to 0 1 2 3 4 from this all the set. So now you are having all the elements in the set. So each and every elements having that closure property, and also identity property, and next universe property. So multiplicative universe. So multiplicative universe is nothing but, so we already know that a for the additive operation, a plus of minus a equals to 0. But for the multiplicative operation, a star a universe equals to 1. So this is what we are going to show here. So what are the universe values of the positive integers? What are the universe values to the positive integers we need to show here. So where you will get the one value in the composition table, so there you can replace the values. So first of all, look at here. So for the 0, there is no one element. So you need to keep it as minus. You need to keep it as dash, or simply you can keep it as minus. And for the 1, so for the first 1, you will get the 1 at one row. So you can rewrite it as direct 1. So here you will get, and for the second column, you will get the 1 in the third row. So third row you will get the 1 here, and here you will get the 1 here, right? And for the third column, you will get the 1. In the second row. So second you need to mention here. And for the fourth one, you can mention this 1 here. So this fourth column, fourth row, you will get the 1, so that you can mention 4 to 4, and 3 to 2, 3 to 2, so 3 to 2, and 2 to 3, you will get here 2 to 3, and 1 to 1, you will get here 1 to 1, so that all these elements are universe elements. So these all the 1 3 2 4 are the inverse elements of this 0 1 2 3 4. 1 3 2 4 are the inverse elements of this 0 1 2 3 4 elements. So this is the way you can perform all the different additive and multiplicative operations to become a field. So from this exercise, from this example, I am going to say that the finite field or field is said to be found only if it satisfies all the associative property, closure property, inverse property, identity property, along with the closure property and commutativity property. So if it satisfies all these four properties with respect to the addition and with respect to the multiplication, then it is said to be, it is a finite field or field, you can say that. Finite field or field, you can say that. So this is the way you can understand with respect to the multiplication and addition operation. So we are having finite field is also called as Gaussian field also. So like the way you can understand this, all the field concepts with respect to the addition and the multiplication operation. So with this, what we conclude that, so we are showing that all the integers of order 5, we are showing that all the integers of order 5 is a finite field with respect to the addition and the multiplication. So this is what we are going to show, and we done to show here, right? So this is the way you can understand. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.